Hello, everyone. Mr. Ford here. I'm going to walk you through an introduction on vectors. We've already briefly discussed vectors in that um, when we talked speed and velocity were different, and velocity is just speed with a direction. So that's the definition of a vector, basically. It's a quantity, a measurement that has both a magnitude, which is the number, and a direction, whether it be positive, negative, forward, backward, north, south, 30 degrees, above horizontal, something like that. So that's the definition of a vector. A scalar is simply just has that magnitude. Things like, let's go back a minute. Vectors, some examples were velocities, displacement, forces, momentum, and then we'll see some others throughout the year. Uh, Scalar quantities only have that magnitude, the number, no direction involved. Things like speed, distance, mass, time, volume, temperature, anything where direction does not have an impact. So a couple things here in the notes. We define vector, we define scalar. Um, so resultant, that's pretty obvious. When we have different vector quantities and we add them together, the result is the resultant. So pretty straightforward there. We will be utilizing Pythagorean theorem, something you learned way back probably in geometry, a squared plus b squared equals c squared. So we're going to be dealing with triangles a lot. Um, this equation we can use to find the angle or direction. I'm going to talk a little bit about um, tangent versus sine versus cosine and what is better, when should you use what, um, in which scenario. So again, we are looking at all the trig functions. And also we see here, this is the unit circle. You may remember that from pre-calc, or if you're in pre-calc now, you'll see that I believe in the spring is when you start to look at vectors. So this is a little mini pre-unit for that. So you will notice on our unit circle, direction-wise, we start at 0. And the angle increases counterclockwise. So something we're going to get into in a little bit is that this is similar to like cardinal directions, like north, south, east, and west. And if we have two vectors, say, we walk east and then we walk north, some people might say, well, you walked northeast. Well, northeast has a specific direction. Northeast is technically 45 degrees north of east, or 45 degrees east of north. So we're not really going to be utilizing cardinal directions that much other than an introductory type lesson in vectors. So usually in physics, we're just measuring angles relative to the vertical or the horizontal, like inclined planes and things like that. So this is just more of a lesson and kind of a continuation or pre-lesson for pre-calc. So we really want to look at those specific angles. So if I were to tell you walk 45 degrees, you know what that means versus southwest. Southwest is a pretty big area if you're kind of not going by that specific kind of middle, the 45-degree angle. But if I tell you walk 150 degrees, you know exactly where to go. All right, so here we go. Let's go back here. So I'm going to go through a couple examples with you, and then you can either pause the video and try the practice or watch the video in full and then do the practice later. So here we have Al. Al walks 3 kilometers east and then 4 kilometers east. So I'm going to start off just by sketching out the diagrams. That's usually the best way, since I mentioned that when we're solving our physics problems, you want to diagram the scenario if it's not already diagrammed for you. So we have Al, he walks 3 kilometers east, and I'm drawing an arrow because technically an arrow is a vector. So the arrow points towards a direction, and the length of that arrow indicates the magnitude or the size. So if this is going to be my 3 kilometers east, and east we can assign, if we're just looking at a piece of paper, east is right, north is north. I'm sorry, north is up, west is left, and south is down. So if I'm going to sketch out then walking 4 kilometers east, that arrow or that vector needs to be a little bit longer. Somewhat relative. We don't have to measure things out. So they are my two vector quantities that I'm going to add up to find out what the resultant is. So it's pretty easy math since they're going the same direction. So that's the same as just walking 7 kilometers east. And we don't need to write east with our measurements of 3 kilometers, 4 kilometers, 7 kilometers, because we have that arrow showing the direction. So then skipping back up towards the top where it says delta x and delta y, this is if we were not going to draw a picture, maybe you were utilizing equations and equations don't understand, or your calculator wouldn't understand necessarily forward, backward, north, south, east, west, so we have to tell it with positive and negative. So since everything is to the right, and we're going to use the idea that positive is up and to the right, and negative is down and to the left, we're going to have Al walk a positive 3 kilometers and then walk a positive 4 kilometers, which that would give us 7 kilometers in total. And in this case, there is no change in the y direction, the vertical direction. So our resultant, the magnitude, the size, the amount, the number is 7 kilometers. The direction, we could say east here because it is a specific 0 degrees or straight right. The equilibrium, the root word equal. So this is going to be the same magnitude, and I've thought through years of taking this off and not teaching you the equilibrium because there isn't a big need for it in physics, but I thought it was still important in that, in this case, let's say you have Al, he walks 7 kilometers east, he goes into a building, he gets disoriented, he comes back out, and he doesn't know how to get back home. So the equilibrium is the same magnitude, so the same distance, if you will, but the opposite direction. So in this case, it would be west or 180 degrees. So if Al understood what an equilibrium meant, he could look at that information and find his way back home. And we'll see that in physics, not only with like displacement and walking, but with forces. So if you want to cancel out a force or a momentum or a velocity, we can kind of look at that. All right, so now let's go for a walk with Tom. Actually, I'm sorry. So you're going to go for a walk with Tom later on your own. We're going to walk with Bob right now. So Bob walks 3 kilometers north. Try and be consistent with my colors. And then he goes 4 kilometers east. And we know that is 90 degrees or perpendicular to each other because north and east are perpendicular. So we can put that right angle indicator in there. And our resultant would be kind of like when we looked at the Toto and Dorothy problem from way back when in the first packet, is just like a snapshot from the beginning. If we started here and we walk towards the end, that becomes our hypotenuse. And you notice I drew, when we had Bob walk, it's called the tip to tail method. So you draw one segment and then you right away continue drawing where you picked up your pen at the head of the arrow. With the exception when you draw your resultant. Your resultant will have like 2 parts of the arrow at the same spot. Anyway, so let's fill in our information at the top. Bob walks 3 kilometers north, so that was my delta y. So north is positive, so I could put a positive 3 kilometers. And then east, 4 kilometers, that's positive. So now I need to figure out my resultant, my orange line here. So what can I do? Well, some of you are saying, well, Mr. Ford, it's a 3, 4, 5 triangle. I learned that in geometry. Fine, it's a 3, 4, 5 triangle. Or if it was not numbers that you memorized or you didn't know about a 3, 4, 5 triangle, you can go use a squared plus b squared equals c squared, Pythagorean theorem, and you would get 5 kilometers. So our magnitude of both our resultant and equilibrium is 5 kilometers. And like I mentioned before, we're not going to say northeast because we don't know yet if it's perfectly 45 degrees north of east or east of north. We don't want to get lost. So we need a specific direction. So what we can do, which I didn't mention, that sometimes when we're drawing vectors or eventually force diagrams, color coding can be helpful, whether it's colored pencils, colored pens. It just seems less chaotic. So this is my origin, just so I can kind of orient myself. So I need to know, relative to 0, what this angle is. So I'm going to kind of erase that for now, because I want you to see that we're just dealing with triangles. So if we have all 3 sides of a triangle, we can find any angle inside. Now I mentioned before, up in the notes, it says to find the angle, we can use tangent, or inverse tangent of y over x. If you want to go that route, that's great. I always tell students, just do what you know. You've passed geometry at this point. So if you like sine, use sine. If you like cosine, use cosine. If you like tangent, use tangent. Experimentally, or in an accuracy-based lab, we probably would want to use tangent because we were given those 2 values. We know them. The 5 was calculated. So what happens if our calculation was wrong? We don't want to have a double wrong kind of situation if we're looking at accuracy-based labs and things like that. But in a worksheet, homework, test, quiz, just use whatever you like. For some reason, I'm not sure why, I tend to use sine. So first off, some people may be noticing, well, what about this other triangle? They are complementary. Once we start drawing, it would be fine to sketch that diagram. You could have Bob walk 4 kilometers east and then 3 kilometers to the north, and essentially he's walking in the same direction as a displacement. So I'm going to look for this angle here so that I can then figure out this portion of my 90. If you wanted to find the other angle, that's fine. If you know about alternate interior angles, that's fine. So like I mentioned, I like sine. I'm not really sure why. It's a habit from high school. So sine is opposite over hypotenuse. So 4 kilometers over 5 kilometers. Notice I'm clothing my measurements with units, and that's how I know that cancels out so that I'll eventually have an angle measured in degrees. I plug that into my calculator, making sure I am in degree mode and that I am familiar with how to plug in information in my calculator, whether it's a $10 one or a $100 one or $50 one. Make sure you know how that calculator works. So when you plug that all in, you get that angle that I've shown is 37 degrees. It makes sense. It looks about that size, right? Or I'm sorry, it's not 37 degrees. It's 53 degrees. So this angle in here is 53 degrees. So we could stop there and just make sure if we tell Bob how to get to certain places, we say, Bob, make sure you walk 53 degrees east of north. We could say that. But then Bob's going to say, well, I don't really understand that because what if I like want to measure north of east? We want to have a same language in physics so that we're all calculating the same number, having the same discussion, and we can kind of communicate that way. So we want to know what this angle is here because it's relative to 0. So since that's a 90-degree angle between x and y of our like coordinate system, we just take 90 minus 53 and we get our direction of 37 degrees. Well, what about the equilibrate? Equilibrate is the same magnitude, just a complete opposite direction. So if you just turn around, you are turning 180 degrees. So in most cases, you will either add or subtract 180 and you'll get your other angle. So in this case, since it's a small angle, we can add 180 and we get 217, and that would be the heading that Bob would need to take to get back home. All right, so at this point in the video, you're going to go and walk with Tom, walk with Jen, and then check your answers in Schoology. And if all is well, you're going to go walk with Bob and Jen again. So feel free to pause, complete those problems, and then resume for the next section. All right, so welcome back. Hopefully you all was well. If not, make a note and we can talk when we see each other again. So this next section, it's a little different. We're not necessarily adding vectors. We are given the results and we need to break them up into components. I'm not going to mention these equations just yet. They will work, but they kind of are conditional, meaning they only work if you draw a certain triangle. So let's go for a walk with John. He's going to walk 5 kilometers at 30 degrees. We don't need to use protractors or anything. It's going to be helpful to sketch in our coordinate system. So this is going to be my 30 degrees here. And what we need to do is break this up into horizontal and vertical components. Eventually, we'll look at scenarios like the next unit with projectile motion, that when you throw an object through the air, say you're just throwing a baseball, it moves in a parabolic path. And we're ignoring air resistance. What is happening horizontally is different than what happens vertically. So we have to use certain equations for vertical motion and certain equations for horizontal motion. So this is why we have to break up that the angled velocity or angled displacement. So again, just like a flashback to geometry, do what you know. You have a side, you have an angle, find out those two sides. Now's time to mention these equations. These equations will only work if you draw the triangle that you see in front of you right now. Now, fast forward a few weeks, we're going to be drawing components on scenarios like, I don't know, a car going up or down a hill, ropes supporting something at angles. So it's going to be kind of wacky, and you kind of draw the angles that you see first. So like we mentioned before with the complementary triangles, you might have seen to draw the components this way and draw this triangle. That's perfectly fine. But when you draw that other triangle, those equations at the top change because you're looking at a different angle, so the sine becomes cosine and it gets confusing. So if you know that you can follow rules and be consistent, feel free to use those equations to get the delta y and delta x, because you have to make sure that you're drawing your components along the x-axis. If not, I would say ignore those equations, cross them out, and just do what you learned from geometry. So going ahead with that, I'm going to start with sine to find this side. So sine of 30 is opposite. Opposite side is going to be my delta y. And my hypotenuse is 5 kilometers. I plug that into a calculator, and I get that delta y side, or the blue side, is 4.3 kilometers. Now at this point, I could just use Pythagorean theorem because I have two sides. For some reason, I don't know. SOHCAHTOA is fun. I mean, it's fun to say, right? So I'm just going to go through and use cosine. So cosine of 30. Maybe I'm scared of squares and square roots. I'm not sure. To find my delta x, I plug that into my calculator, making sure I'm in degree mode, and I get 2.5 kilometers. And I'm going to stop and see if that makes sense. So sure, that's believable. Maybe I didn't draw it to scale. Maybe my 30 degrees needs to be a little bit bigger. I will note, if you are going to draw a right triangle, make sure that it looks like a 90-degree angle. I've had students do this and say, Mr. Ford, there's my right triangle. So I say, student, well, where's your right angle? Just say right there. Right where? And they'll do this. I say, well, it's right here, Mr. Ford. Don't you see the right angle indicator? Try and draw it the best that you can to be a right angle. Feel free to use straight edges. I don't think you really need to use a protractor, but feel free to if you would want to. So that's the next part, is just breaking up components, or breaking up resultants into components. It's just what we did earlier in reverse. So go ahead and take a walk with Amy, Abe, and Bob. And you can pause the video and then check your answers in Schoology, and then resume the video to find the next section. All right, so this is where it gets a little bit, not difficult, but more meticulous, more work. Because what we're going to have now is two resultants that we need to add together. So two vectors that are not in either the x or y direction, and we have to add them together. So what we're going to need to do is break them up. So let's sketch this out first, sorry. So we're going to have Jeff walk 2 meters at 60 degrees, so maybe something like this. And do not write this, so stop drawing. Some people would say, all right, well, he walks 2 meters at 60, and then he's going to go 4 at 120, so that's kind of the other way. Right? That does not make a right triangle. You may have learned some things to do in pre-calc. If you took pre-calc, I've seen students do like stuff like this. It gets confusing if you try to do it all in one, especially if there's going to be multiple vectors that we need to add. So we're going to draw it like this. So 120 is, maybe I drew that angle a little bit too big. 120 is like about like this. Make that a little longer so it looks like 4 meters. So here's my 4 meters. So what we're going to have to do, just like we just did, is break up each one into its components and then add them together. So this is going to be a while, but just stick with me. It's not difficult. It's what you did in geometry. It's just a little bit meticulous. So I'm going to break up each one into components, horizontal and vertical. This is my delta y, that's my delta x. Same thing with this one. Delta delta y, delta x. I'm just putting that, just people typically get your x's and y's confused sometimes. And let's change colors a bit. I know that this is, oh, I forgot to fill out my angle, 60 degrees and 120. So again, 120 is relative to the right being 0. So this big angle here is 120. So if I subtract that from 180, I get this interior angle to be 60. And I can use sine, cosine, tangent now. So let's see. Since this starts off with delta x's, I'm going to do cosine first. So for, let's see if I can split this in half. Cosine 60 adjacent over hypotenuse, so delta x over 2 meters. I plug that into my calculator, and I get that that is 1 meter, so this side is 1 meter. Then to find my other side, I'm going to use sine of 60, so now I'm looking at the other side. So opposite is my delta y. I plug that into my calculator, sine 60 times 2 meters, and that's going to be 1.7 meters. So my 1 meter positive plus my 1.7 meter positive is going to be a total delta x, or I'm sorry, wrong part. Getting ahead of myself because that was delta y positive. All right. Now let's go with our 4 meters. So cosine 60 delta x over 4 meters this time. Plug that into my calculator. And I'm going to get 2 meters here. But it's moving to the left. So if we said to the left is negative, again, we're summing, we're getting a total of negative 2 meters. So you notice I wrote 2 here and negative 2 here. The reason why in my diagram I didn't indicate the negative, because I don't need it. I already have an arrow pointing to the left. But in an equation or mathematical equation, I can't like put an arrow in. I can't insert that into a calculator. So I have to indicate that direction with a negative. Now you need to kind of commit to the type of person you are. For some reason, again, it could be from something I did in high school or college, I tend to not put positive and negative signs in my diagrams since I have arrows. But I've seen students time and time again, they say, oh, my delta x is 2, I'm going to plug that into an equation. But they forget to look at the arrow. So if you think you're going to be that type of person, it might be good just to be a little redundant and say that that's a negative 2. So you don't make that simple mistake. So then to go find my delta y, plug that into my calculator, and I get a positive 3.5 for my vertical delta y. So now I can sum both of my displacements in the x and y direction. So I get a negative 1 meter and a positive 5.2 meter. And if at any point this goes a little bit too fast, feel free to rewind. Also, there are some steps and instructions here as well. All right, the next thing. So we broke up our components, our 2 meter and our 4 meter vectors. We broke them up into x and y. We summed them, and we have a x and y. So now it's basically what we started off this packet doing. We would simply sketch out our -1. Actually, let's get that a little bit lower here. -1 meter. And my positive 5.2 meter. And I'm making sure I draw that so it makes sense. And the resultant is my hypotenuse. Not really happy with that line. Let's make it look like a triangle. There we go. Where here's my right angle. Not my best work, but anyway. So you have two sides, no angle. How do you find the hypotenuse? Pythagorean theorem. A squared plus b squared equals c squared. Plug that into your calculator. And just by coincidence, not by coincidence, but it's really close to the other side. And that makes sense because it's going to be like a skinny triangle, right? This is only 1 meter, and the height or the vertical is 5.2. It just so happens to be really close. All right, so we have the magnitude of our resultant. Now we have to find direction. And again, direction needs to be relative to 0. So we're going to eventually be looking for this big angle here. So I'm going to find this angle. You could find the other one. So I pause for a second. TV went on. Don't want the TV on. So you could find this other angle up here. It's up to you however you see geometry. So I have all my sides. I'm looking for an angle. I'm just going to switch things up, and I'm going to use tangent this time. So tangent theta, 5.2 meters over my 1 meter. So if I plug that in, the theta that I found, I've had discussions with students in the past that like theta is like the real angle. I'm just going by what I have drawn here, just so we're clear. So the angle inside here is 79 degrees. And I'm looking for what this bigger angle is. So I need to subtract, so if straight left is 180, if I do 180 minus 79, I get my resultant direction. It's not really clear of these are just the directions, since I already have my magnitude. That big angle is going to be 101 degrees. And the equilibrium, if, so who we have here? Jeff. We now know where to tell Jeff to walk. Jeff, you're going to walk 5.3 meters at 101 degrees, since we're starting from relative to 0. He gets there, and he needs to get back home. I know 5 meters is not a far distance. You could probably see where to go. But he's going to go 281 the other way to get back home, because we simply just added 180. So at this point, you can go ahead and try the remaining walk with Bob, Lisa, and John. So that should complete the assignment worksheets 1 through 4 of the vectors packet. And again, if at any time you need to pause the video, go back, rewind, check the solutions in Schoology, make note of any questions for when I see you next. We can have those discussions. Have a great day.